Good morning, I'm Carly Sullivan Crouch.
And I'm Abby Honabarger.
And first off, we'd like to thank you, Professor Dr. McElhenney, for letting us come share some of our results from our ocean acidification experiment with you.
So first of all, we need to ask, what is ocean acidification? Well, according to the NOAA, or the National Oceanic and Atmospheric Administration, ocean acidification is when carbon dioxide is absorbed by seawater, thus causing chemical reactions to occur. These chemical reactions reduce the pH of the seawater as well as the concentration of carbonate ions. So, as you can tell by the picture above, the carbon dioxide that is a result of our fossil fuel burning is being absorbed by the water, which causes a formation of carbonic acid. Carbonic acid further breaks down to bicarbonate and carbonate, which releases hydrogen ions. And the increase in hydrogen ions in the water is what causes this reduction in pH, causing the ocean to become more acidic.
So you may be wondering, where is all this carbon dioxide coming from? And I have the answer for you. Anthropogenic causes, which means caused by humans. According to Woods Hole Oceanographic Institution, the world's ocean water has become more acidic since the beginning of the Industrial Revolution. This is when human beings began burning mass amounts of coal and other fossil fuels. Since then, scientists and researchers have concluded that ocean acidification is the direct consequence of increasing levels of carbon dioxide into the Earth's atmosphere.
So as Carly stated before, this ocean acidification has been occurring since the Industrial Revolution, where the ocean pH went from about an 8.2 to an 8.1. And according to Bennett from the NOAA, it's expected to decrease another 0.3 or 0.4 pH, which will bring it down to about 7.8 or 7.7.
So past studies show that the concentration of carbon dioxide in the atmosphere prior to the Industrial Revolution was 280 parts per million. But since then, with the increased use of fossil fuels, the number is quickly approaching to 400 parts per million. According to WHOI, scientists have calculated that the ocean is currently absorbing about 1/4 of all the carbon dioxide humans are emitting. Research also shows that half of the anthropogenic carbon dioxide levels in the ocean are found in the upper 400 meters of the water column, thus causing the most harm in the epipelagic regions of the ocean, which is really pertinent to your class. I spoke with Dr. McElhenney before coming and presenting to you, and she said you're going to be learning a lot about the different zones of the ocean soon, one of them being epipelagic. And when you learn that, you'll learn that a lot of marine organisms are found there, and they're vast, from very small things like zooplankton, which will be affected by ocean acidification, and very, very big organisms like whales that will also be affected because they won't be able to consume the proper nutrients if organisms can't thrive and survive. So another part of the ocean that is also affected by ocean acidification is the deep ocean, and this is because of the mixing of water by upwelling and downwelling. But for now, the open ocean has actually resisted changes in pH, but scientists expect that by the end of the 21st century, we will be seeing some of these fluctuations that Abby discussed previously.
And it's true, as humans, we benefit from the ocean's capacity to hold excess atmospheric carbon dioxide. However, this could backfire on us very quickly because this atmospheric concentration of carbon dioxide is now higher than it's ever been. Our oceans cannot continue to absorb any more carbon dioxide at the current rate without undergoing significant changes in its chemistry, biology, and even the ecosystem. So Carly and I performed several trials of an experiment for ocean acidification to test the changes in pH, shell mass, concentrations of bicarbonate and calcium in the water. And to do this, we took two separate round-bottom flasks. We placed in them roughly the same amount and the same type of seashell. We then filled them with a specific amount of artificial seawater, which we will call ASW for further reference. One we left non-carbonated, and the other we purged with CO2. We then let them sit on a stir plate for a week, capped to prevent evaporation and contamination. And we came back a week later and we tested all of these changes to our experiment.
So one of the first things we looked at and compared between the ASW, the carbonated and the non-carbonated water samples was pH. So did this by using a pH meter that was calibrated using calibration standards. And we found out that the original pH level of the ASW was 6.35, as indicated on our slide. The pH of the non-carbonated sample was 6.59, and the pH of the carbonated sample was 6.00. Now, because of our previous knowledge, we expected that the carbonated sample would have a lower pH because it included a higher concentration of hydrogen ions. But there was a bigger difference between the non-carbonated sample and the ASW that we expected, and this could be due to experimental error, us not cleaning off the calibration pH meter correctly, or it could be due to the fact that the non-carbonated sample included the shell and that the shell had slightly broken down, causing the solution to become a little more basic.
So another aspect that we tested was the shell mass from the original shells that we had placed in our samples. So the sample that was non-carbonated showed very little degradation of the shells. They saw about a 0.49% loss in mass, but the shells that were in the carbonated sample saw about 4.38% loss in mass, which is much greater than the non-carbonated sample. And this is due to ocean acidification, the breakdown of the shells, which is a huge problem for our coral reefs. We also tested the bicarbonate levels in the water. And as you can see on the graph, the different colored bars are mine and Carly's samples averaged out. And the ASW and the non-carbonated sample have roughly the same amount of bicarbonate. But if you look at the carbonated sample, it has a very high concentration of bicarbonate. And this is due to the increased amount of hydrogen in the sample. The hydrogen has a very high affinity for carbonate, and when they bond, they form bicarbonate in the sample.
So in addition to testing the concentration of bicarbonate within our samples, we also tested the concentration of calcium ions. And as you can see, the carbonated sample has a higher concentration of calcium ions, and this is due to the fact that the bicarbonate had already binded with the excess hydrogen, leaving these excess calcium ions behind based upon this equation. Calcium carbonate plays a significant role in the building of the skeleton of many calcified organisms within the ocean. And so this is why we really looked at this equation here. And as you can see, CaCO3 disperses into calcium and carbonate. And because these two aren't binding together, it leaves us with an excess of this calcium ion. So as previously stated, this calcium carbonate is the building block for the skeleton and shells of many marine organisms, such as oysters, clams, mussels, snails, but most importantly, our coral reefs. With ocean acidification on the rise, it is causing many parts of the ocean to become undersaturated with this calcium carbonate, which will likely affect the ability of many of these organisms to produce and maintain their shells or find shelter, like the epaulet shark, which will be discussed later in this. And so as you can see by this picture, the coral reef is a habitat to several organisms, such as fish, and about 1 in every 7 Americans have fish as their main source of protein. And so could you imagine if all these coral reefs were destroyed and died out, that would also affect the survival of these fish. And could you imagine millions and millions of people all across the globe not having a source of protein in their diet? See, the thing about this is that ocean acidification doesn't just affect the organisms found within the water, but it affects people just like you and I.
So as we stated before, our experiment was designed to study the effects of carbon dioxide levels in the ocean, but we can't study the ocean itself. It's much too vast. So we knew that there were some limitations to our experiment. And according to the EPOCA, there were some variables we couldn't account for, such as pollution, fresh rainfall, the currents, just weathering for the ocean in general. All of these factors would play a role in varying pH levels, bicarbonate, calcium levels, based on where we took our samples, what type of weather was around when we decided to do our experiment, many factors that we could not personally account for.
So very little research has been done on organisms that are non-calcifying. However, recently, very recent actually, at the very beginning of March, Dr. Jody Rumer and colleagues did an experiment regarding ocean acidification on the epaulet shark. Now this might be really interesting for your class as marine biology students. I've heard you've talked a lot about sharks and different types of bony fish and cartilaginous fish. So you might be interested on how organisms outside of those calcifying organisms might be able to survive. So Jody Rimmer and colleagues found out that the ocean acidification effects have actually no effect on the survival of these epaulet sharks, which is very interesting. However, they did conclude at the end of their research that because of the habitat these sharks live in, which is the coral reefs, they would be just as vulnerable as any other organism in the sea. As you can see, ocean acidification is a huge problem. So what does that mean for our future children, grandchildren, or even great-grandchildren? According to the IPCC, the Intergovernmental Panel on Climate Change, economic and population scenarios predict that atmospheric levels of carbon dioxide could reach 500 parts per million by the year 2050, and even 800 parts per million or more by the end of this century. This will not only lead to ocean acidification, but a plethora of other monumental issues as well, such as global warming, other various types of climate change, and even the ice caps melting. So, you may be wondering, what can you do on a day-to-day basis in order to reduce your carbon footprint? Well, I'll let Abby tell you of the small, simple things you could do to reduce your carbon footprint daily.
So one of the main things you can do to reduce your carbon footprint is to reduce the emissions from your cars. So a great way to do that is by carpooling, taking public transportation, reducing the amount of vehicles on the road. If you're in close enough distance, like especially here on a college campus, you could walk or bike from class to class, or instead of driving your car from building to building. One of the main things we should do as a nation is have our government implement a law mandating that we need to have our car emissions checked at least once a year, just to make sure the level of car emissions is staying low, and if it is higher than normal, getting it fixed so we can reduce our carbon footprint. There's also little things you can do in your house every day. Turning off lights that you aren't using at the time, unplugging all chargers that you aren't using. Even if your phone isn't plugged into the end of the charger, it's still taking power from the outlet, and that's just a waste of energy. So that's something, very little things we can do on a day-to-day basis to keep our carbon footprint low. And if you are curious, and I highly encourage it, there are several carbon footprint calculators online. If you want to go through and input your information just to see what kind of impact you're leaving on the world. It even has a feature where if you were to continue, if everyone were to live the life that you lead, it would take how many planets to support you. In our case, it would take me about 6 planets to sustain the life that I would lead if everybody chose to live the way I did. So that's just a real eye-opener for myself, to just rein it in, use less electronics when I don't need to, and just be more self-conscious with the environment.
And perhaps the best thing that you could do is to educate yourselves and then to educate others, and that's what we've come to do today. And as though it may seem that ocean acidification has recently emerged as a hot topic in the world of science, it has quickly raised concerns, serious concerns about the health of the oceans and the organisms that inhabit it. And eventually it trickles down to us, because many of these organisms are source of our food, our medicine, and various other things such as cosmetics and even recreation. So we hope that we've enlightened you today, and we hope that you can take what you've learned and educate others. Thank you for your time, and thank you, Dr. McElhenney, for giving us the opportunity to talk to your class. And also a huge thank you to Dr. Booth from the University of Mount Union for contributing to our education. Thank you, and have a great rest of your day here at the University of Mount Union.